Hi, I'm Kevin Knuckles. I'm a graduate student here in the Yazdani lab. I'm a fourth year, and I'm excited to show you around this nanoscale microscopy lab. Yeah, so generally the Yazdani group is split up into a number of sub-teams that manage microscopy facilities. We're doing scanning tunneling microscopy. I have an atomically sharp tip and a sample that I want to study the electronic properties, and I bring that tip within about a nanometer of the surface and measure the conductance between the tip and the sample to tell about the electronic properties of the system. So here is the ultra-low temperature scanning tunneling microscope. This is Ali Yazdani's newest microscopy facility, which I had the opportunity to work with a number of postdocs to help build. It's a 2.5-story microscope consisting of a floating room and a number of chambers that sit in this top room and a large cryostat. Maybe we can go inside. Yeah, so SDM is all about cleanliness, so we have a number of vacuum chambers here that we use to introduce samples, to clean them, and then to plunge them into our dilution refrigerator SDM, which sits underneath this table. So this whole room that you're standing in right now is a floating room. We've got it rested right now so that we can come inside, but it's about a 20-ton concrete plinth. This is a 7-ton granite table. And the whole reason why we have these things is that SDM is extremely vibrationally sensitive, that the conductance between a tip and sample is exponential in the junction's distance. And so small vibrations, small oscillations with people walking outside, with elevators running in the building, or with dump trucks placing down garbage cans. This all affects the tunneling current and affects my measurements. And so we want to use very, very large inertial masses, which essentially act as damping sources, that the transfer function of vibrations into my system is very poor. So this is, again, the newest microscope in the suite of instruments that the Yazdani lab has. It's a dilution refrigerator microscope. So this means that it has a dilution fridge and a mixing chamber that cools down our sample and our system down to millikelvin temperatures. Our electron temperature is around 180 millikelvin. It's also got a vector magnetic field, so I don't know, you want to come down. So like all within this dewar here, we also have a poster over there that we can talk about. So all within this dewar here is a liquid helium bath that cools our system. It's a dilution refrigerator. And then there's also a magnetic field that has 9 Tesla out of plane and then 1 Tesla in any direction. Generally, we design this microscope to characterize device samples. I want a 2-dimensional sample that is gate tunable. And when I do spectroscopy as a function of gate, I can look at correlated phases of matter that depend on the density of the sample. So this is a second instrument in the Yazdani group. This is called the Vector Field Scanning Tunneling Microscope, VFSTM. It has a cooling system, a 1K pot system that gets down to 1 Kelvin. It also has a vector magnetic field with 6 Tesla out of plane and 1 Tesla in any direction. And we use this also for device capabilities. So this is a lot of office space that we use. The Yazdani group benefits a lot from just collaboration and talking about science with chalkboards. And so it's nice to have a series of desks that are all kind of in close proximity to one another, and some space to hang out and chat about physics. So this is the chemistry room. We use this for a number of sample preparation processes. In general, the name of the game is to get a very clean, fresh sample into the SDM with an atomically clean surface. And so we have a number of methods that require single crystal preparation as well as device fabrication that occur in this room. Yeah, so this is the lower floor of the microscopy facility. We have essentially a 2-story situation where the upper story contains all the vacuum chambers, it contains all the science chambers, and then down here is vibration isolation equipment. Yeah, So again, STM is very, very vibrationally sensitive. And so what I want to do is to have my facility as far removed from any small perturbations of the outside world. And so what I do is have a large floating room. This is a concrete room that's separated from the walls and is held up by these enormous air pistons. So there's 6 of them. They have rubber diaphragms on the top that push the room just a very small amount above where it's being seated right now. And the concrete plinth is tens of tons in weight, and so essentially it has a very, very low natural frequency. A mass on a spring would tell me that the oscillations that are able to be transmitted, the transfer function is very poor in the high frequency range. And so essentially this is a really nice way to separate ourselves from the walking that happens in the lab, the elevators, and the trucks that drive on the road outside of our lab. Here. So all of our experiments are done at low temperatures. This is largely for energy resolution. That the resolution I have in spectroscopy is proportional to the temperature of my setup. And so we need to cool everything with liquid helium. And we have a number of apparatuses in the Yazdani group to produce liquid helium for ourselves in the large quantity that we use it. So we have these purifiers here. These are in conjunction with some compressors that take helium gas that is at ambient pressure and compress it into a very small volume. We have liquefaction cold heads. This effectively, through the Joule-Thomson process, causes a very high pressure helium gas to turn into liquid helium. And then we have these mother dewars that contain something like 500 liters each. So generally, I'm pulling liquid helium from here and transferring it into my instruments upstairs to keep them cold. So this is what's called a transfer station. So generally, I am interested in correlated phenomena in 2 dimensions. And so very atomically thin materials can be stacked and exchanged and twisted into one cohesive mega material called a van der Waals heterostructure. And I use this kind of setup to do so. So I'm using this facility to put together flakes of 2-dimensional materials into a transistor type geometry in order to do scanning and tunneling microscopy on particular regions where there are interesting 2-dimensional materials stacked on one another. Yeah, so we use like some micro manipulators and this optical microscope to position polymers, position 2-dimensional materials with respect to one another, and build up devices, all in this kind of ambient condition setup. Yeah, thanks for joining us for this tour. It was really fun to show you all around our lab here. I hope you all join us at Princeton Physics.